Welcome, ladies and gentlemen. Today we're going to look and dive into a little bit of basic nuclear chemistry. So we're going to get into the ideals of how isotopes decay, why certain isotopes decay in different patterns than others. Really dive into the purpose of fission and fusion and all of that good stuff. So we'll take a look at that a little bit later on. But first we have to start off with the basics. And that's what we're going to look at here today is just basic nuclear chemistry. And our goals today, you should be able to understand why certain isotopes undergo radioactive decay and why some don't. And then we're going to take a look and analyze some decay problems. Hopefully, you'll be able to take a reactant, know what type of decay it undergoes, and then showcase that decay and fulfill a radioactive isotope chemical reaction. So we'll look at that and show that a little bit later on. So the first thing we want to talk about is what's called nuclear stability. And some isotopes are more stable than others. Basically, isotopes are either stable or unstable. If they're stable, they will not decay. I used an analogy earlier when we talked about building Legos. And if you build small things with Legos, they tend to stay together. But if you start building larger and larger models of things with Legos, they tend to fall apart or break more easily. You have to be more careful with them. And the same thing works with atoms. If you have more neutrons and protons, the protons tend to repel themselves more, and the neutrons really can't hold the atom together quite as well anymore. So you start to see some decay. If it's too high or too low, the nucleus is not stable and will decay. It'll release some form of a subatomic particle, whether it releases either an alpha particle or a beta particle. That's what we'll talk about a little bit later on. But the purpose is to understand that isotopes are either stable or unstable. And if they're unstable, they're going to release some protons or neutrons so that they can become stable. Very much like how a Lego model will break apart into pieces until it becomes more stable so it won't break apart anymore. If you look at the chart here on the right, it just shows you there's a zone of stability, a ratio of neutrons and protons. And if you look, you'll see that there's an area where the neutron to proton ratio is 1, the neutron to proton ratio is 2, and you can see there's a zone of stability kind of right there in the middle, somewhere around 1.6 or so neutrons to protons. So there's an area of stability where we see the most frequent isotopes that are stable, and if they are stable, they will decay until they get into that zone of stability. The process of radioactive decay is the loss of nuclear particles due to an unstable nucleus, and it can be lost in several different ways. We can lose them through alpha particles, we can lose them through beta decay or gamma radiation, positron production, and electron capture. Now we could talk about all 5 of these, but the 3 that I'm primarily going to talk about today are alpha particles, beta decay, and gamma radiation, because those are the ones that are the most frequently seen at this level of chemistry. The first is what's called alpha decay. And alpha decay typically occurs in rather large nuclei. So if you look at the examples that are given, we have radium-222, and we have plutonium-239. And if you look over time, plutonium-239 will decay into uranium-235 plus a helium nuclei, also known as an alpha particle. So we see that alpha decay is the release of a helium atom from the nucleus, involving 4 protons and neutrons and 2 protons. So 2 protons and 2 neutrons are being released from the nucleus when an alpha particle is released. So you can see here how alpha decay works. We start off with an unstable nucleus, and then it becomes more stable once it releases that alpha nuclei or that alpha particle. All right, so that's alpha decay. Beta decay is essentially the process which converts a neutron into a proton. So we use the beta symbol with a 0 as the mass number and a -1 as the atomic number. And so you can see a couple of changes that occur here. For example, the one on the right where radium-228 decays into actinium-228. All right, really doesn't change much except it changes 1 neutron into a proton, so we actually gain a proton from beta decay. More frequently, you see beta decay with smaller nuclei because there's not quite as much to be released there, so the nucleus becomes more stable much faster that way. Tritium, if you look below, hydrogen-3 decays into helium-3 through the transition of a neutron into a proton. So beta decay essentially converts a neutron into a proton, and again, it's the same process as in alpha decay. We take our reactant particle, and then we undergo the process of decay, which gives us our product particle. Now, gamma radiation is the release of a high energy photon, so it really doesn't change the mass number or atomic number. Gamma radiation is typically released in higher mass particles. This is the type of radiation that can be very dangerous for you because it's able to actually penetrate through concrete. So this is the type of radiation that causes a lot of the cancers due to things like nuclear fallout or if there were a nuclear disaster. Like for example, the one that happened in Japan. The gamma radiation is the one that's the most dangerous. So we don't typically use this a lot when we are doing the math formulas or the chemical formulas because it's simply that there's no change in mass number or atomic number. So we don't see a release of that. But there is a release of photon, and that high energy electromagnetic wave is what causes a lot of the cancer after nuclear disasters. So I just think that it's important to know. A lot of times this is also released with a beta particle as well, but again, we won't be showing that in our chemical reactions or equations. So if we look at the two questions that are listed here, we want to undergo alpha decay of lawrencium Lr265. So we need to do a little bit of work here. And we need to start off by taking the hyphen notation and converting that into nuclear notation. So if you remember, lawrencium, we just write as Lr. And again, we want to make sure we write out our notation correctly, so 265. And on the bottom here, we're going to write out our atomic number, which is 103. And again, it undergoes alpha decay. So if we look back and remember, alpha decay, which you can just write just like this, or you can write it as helium, however you want to do it, has a mass number of 4 and an atomic number of 2. And so the rest of this is essentially just like a math problem here, all right? Because we need to find out this number, and that will help us determine the chemical element that we're going to write out. And if we write this like a chemical equation, this is essentially saying that 265 is equal to 4 plus blank, or 4 plus x. So if you think about that, 265 equals 4 plus x. X is going to be 261. All right? And then if you look at the bottom one, 103 is equal to 2 plus 101. And if we look at 101 on the periodic table, it's Mendelevium, and we would just write MD. And that's it. You're done. That is the answer to your problem there. All right? So if we scroll down and look at the next problem, it's asking for the beta decay of bromine 82. So again, write this out in the nuclear notation. And bromine's atomic number is 35. And write our arrow. And now we're going to undergo beta decay. And if you remember, beta decay is indicated by a beta symbol, which is just like this. A 0 for your mass number, and -1 for your atomic number. And the process is exactly the same. Actually, this one's actually a little bit easier because there's less mental math you have to do. 0 is equal to, 82 is equal to 0 plus 82. And then 35 is equal to -1 plus 36. And if you look on your periodic table, 36 is krypton. And you would write it out just like that. And again, that's your answer. All right? Pretty simple, pretty straightforward, agreed? So let's move on and do a couple more practice problems, and then we will go from there. All right? So again, we're going to take a look at a couple more nuclear transformations. And so we're going to start off with show how uranium-235 undergoes alpha decay. So again, start off with uranium-235. We got 235 as our mass number. 92 is our atomic number, and uranium is U. Draw our arrow. And we're undergoing alpha decay. So if you remember, alpha looks like this. 4 and 2. And now we just do the math. So again, 235 is equal to 4 plus, hopefully you're smart enough to know that's 231. And 92 is equal to 2 plus 90. And then you would just look on your periodic table, and 90 is thorium. I like thorium because it reminds me of Thor, which is the Norse god of thunder. I'm probably wrong on that, but who cares? I teach chemistry. I'm not supposed to know that kind of stuff. And there's your answer. Okay? Thorium. I didn't say it right. I'm sorry. Thorium 231 is your answer. Last one. Asked you to demonstrate lithium-7 undergoing gamma decay. So let's start off by writing out lithium-7. So Li7. And the atomic number is 3. And in case you don't know, gamma looks kind of like a Y almost. But if you remember from our notes, no change with this. So you're going to write the exact same thing you started with. And that's your answer. Okay? So again, just take it one step at a time. Look at what nuclear transformation you're undergoing, and then write out your response, just like you would any type of math problem. It's very easy to do. But again, this just showcases how unstable nuclei become stable nuclei by releasing some type of radioactive particle. So hopefully today you understand why isotopes undergo radioactive decay and analyze some decay problems. You should be able to perform any of the decay problems that me or any other teacher would be able to give you. So take this knowledge with you, and next time we will talk about fission and fusion and how radioactive decay has we've been allowed to harness that energy and utilize that to power homes and create wonderful weapons of mass destruction. All right, we will talk to you guys later. Have a great day and enjoy the rest of your afternoon. We'll talk to you later, guys. Bye.